Truly, everyone should work on Atlas.
Or be Atlas adjacent, understand the mechanics.
It's all right. Well, hello everyone. Today is our first in-person interview.
Beautiful.
And I am joined by Mr. William Rettie, a grad student at Carleton University. Hi, Will.
Yes, thank you. Hi, thanks for having me.
You're very welcome. Would you mind introducing yourself, talking about who you are?
Yeah,
and
absolutely.
What you do?
Okay, hello listeners of the Quantum Mic. My name is William Rettie. I'm a third-year grad student here at Carleton University. I work with the Atlas experiment at the LHC, and I have about 3 years left to my degree right now.
That's exciting.
Yeah, it is exciting. I just got an NSERC grant, which is great, which starts this semester. So I'm very happy to get a bit more funding than grad students are used to. But it's a fun time.
That's fantastic. Yeah. All right, so you work on Atlas.
Yes. Do you want me to explain kind of the LHC Atlas to your audience? I don't know how well-versed they are.
I am an Atlas guy,
right?
As well. I mean, we are essentially colleagues.
As everyone who is, watching this video should be, truly.
Truly, everyone should work on Atlas.
Or be Atlas adjacent, understand the mechanics.
It's all right. For people who have not heard of Atlas and have not heard of the LHC,
absolutely.
Would you mind talking about vaguely what the LHC is and what Atlas is?
So the LHC is the Large Hadron Collider. It is the most complicated machine ever built by man. That's a very cool little tagline that I like to add. It's this big particle accelerator in Geneva, between the Geneva and France border.
It's the French, yeah.
Geneva and France, yeah.
It goes under Switzerland and into France.
It's like halfway through between both countries. It's 27 kilometers in circumference. And essentially what we do is we take protons, so individual proton particles, and we accelerate them at 99% the speed of light in one direction. And then we do the same thing in the other direction. And what we do is we take these beams of protons and we collide them together. Hence the Large Hadron Collider.
Of course.
So kind of like children playing with Legos, we just smash things and see what happens. And what occurs when we accelerate these particles at such high speeds is that we reach energies that are allowing us to see very exotic physics phenomena. So you might have heard in the news or in other summaries that we actually recreate the environment of the Big Bang about maybe a second or so, I think, after the Big Bang. And this allows us to see, like I said, a lot of exotic, rare things that occur in nature. So for example, in 2012, they found the Higgs boson, which was a big deal. It won the Nobel Prize. Peter Higgs specifically won the Nobel Prize. And since then, essentially, we've been trying to justify keeping this machine going because it does cost a lot of money with a lot of government oversight and interpersonal communication and whatnot, coordination. And so what we're trying to do now with this Large Hadron Collider is, okay, we found the Higgs. And we have this thing called the Standard Model. Hopefully, I'm not going.
No.
Okay, great.
This is for it, right? If you say anything that I feel like the viewers may not understand, I'll just ask for clarification.
Fantastic. That's great.
It's perfectly good.
So right now, what we have, kind of as the main, how would I say, status of modern particle physics, is we have this thing called the Standard Model. So this thing called the Standard Model is basically an explanation of most things in the universe. So basically, electrons, all our fundamental particles, we understand to a very high degree with this thing, which we call the Standard Model, and it's able to predict a lot of things in the universe. Now, if this perfectly predicted everything, then that would be fantastic, and we'd be done with physics, and we just measure everything like Planck said in the 1900s. But unfortunately, there are a few holes in the Standard Model, things such as like neutrino mass, which it doesn't directly predict. And so what we need to do is break the Standard Model to be able to understand its limits. And what this is kind of referred to as is physics beyond the Standard Model, or BSM. And these days, the main goal of particle physics is to search in different areas of BSM. And the Large Hadron Collider is a really good tool to do this because with such exotic physics phenomena that are produced in these collisions, we get to see a lot of things that could potentially break the Standard Model. So far, unfortunately, we've seen nothing. And I can get into what my thesis focuses on. Hopefully, we'll see that.
That was going to be the follow-up question.
Well, there we go. But so far, unfortunately, we're about, 14 years since the discovery of the Higgs boson and nothing yet.
Oh, dear God, it is 14 years.
Listen, in terms of physics, that's not too far or too long of a time frame. These things take time. Analyses, for example, just my analysis, this, rinky-dink thesis is going to take 6 years. So that's already almost half the time. So definitely, 14 years is not too long. But we do need to hopefully see something soon. And if not, as some people might see in the news, we're trying to build this Large Hadron Collider, which would be 100 kilometers in circumference.
Yeah.
But that's a whole other story.
The Future Circular Collider.
Exactly, yeah.
As
The
it's cur-
bigger
as
one. Just give us a bigger one and we're
as
good.
it's currently named.
Exactly.
Of course, to be renamed.
Exactly.
All right. So you're a grad student,
Yes.
which means you do research.
I do research
for a
full-time.
professor.
Yes, yeah.
So
Dr. Jesse
what is
Hallman,
your?
yes.
We all love Dr. Hallman. So what are you currently working on?
Right. So my thesis focuses on essentially being a dark matter search. So I'll give kind of a rundown of dark matter first, and then afterwards I'll discuss my specific thesis.
Yeah.
Right. So the idea with dark matter is going back to this idea of our standard model. It predicts and explains the universe quite well. Now let's assume that the entirety of our universe is made up of matter. So this stuff we really fundamentally understand. So this chair, my hand, this microphone, it's all made up of matter. Now, if that's the case, if the universe is 100% made up of matter, then when we look out at galaxies, we should be able to predict the way that they move.
Mm-hmm.
So let's say some astronomer looks out, sees some specific galaxy, and says, okay, it should be moving to the right. Now, what happens is that a lot of smart astronomers look out into space, they look at this galaxy, and oh no, it's moving to the left.
Mm-hmm.
So a way to think about it is if you were to see, for example, if we look out this window and we see leaves rustling and a man holding his hat and a woman's hair flowing, you'd say, oh, it's windy outside. There's wind.
Mm-hmm.
And in that same way, when we see these galaxies move to the left, we say there's some sort of cosmic wind interacting with the matter in these galaxies that makes it so that they're moving to the left. And this is what we call dark matter. It's this sort of ephemeral cosmic wind that we really have no understanding of, but we know it's there because we can physically see the ramifications of its existence.
Mm-hmm.
So that's what dark matter is. This idea of cosmic wind, this stuff that we know is there, we can see it interacting, we have no idea what that is.
Yeah.
Now, my thesis focuses on one specific kind of idea behind what dark matter could be. There are a multitude of ideas. There's this thing about axions. There's the WIMP theory, which has been researched for 20 years now. I think
that's one of like the big ones.
Yeah,
like the one that everyone talks
exactly.
about.
Yeah, the popular one, the WIMPs. Yeah, exactly.
Because we got rid of machos.
Right, exactly.
That was the older version.
Ironically, so the WIMPs have
the WIMPs have won.
Absolutely.
For now.
And so my thesis focuses on this idea of having a dark sector. So instead of dark matter being this kind of fundamental particle that exists within our universe, we would assume that it exists in this sort of parallel universe, which we call the dark sector. Now, what happens is that when we produce a certain particle in the Large Hadron Collider, in my case, we assume it's the Higgs boson. When we produce the Higgs, what I'm banking on is that this Higgs is going to interact with the dark sector in some sort of way and decay back into our universe. So basically, it's going to be a messenger between this dark sector, which we essentially can't interact with except for this Higgs boson, and our universe, which we see in our detector. What happens is that when this Higgs boson decays back into our universe, it's going to deposit a very unique signal in our detector that we'll be able to see. So usually, as a quick rundown of what we see in our detector is this thing called jets, which is kind of when you have very energetic particles that interact with each other, they kind of collimate into this very hard object or very energetic object that we're able to distinguish as a jet. That's what we call those jets. Rather, what I'm looking for is something called a soft unclustered energy pattern, or SOUP. The SOUP theory is what we call it. And instead of being a very hard jet, kind of like a triangle in our detector or a cone, what we'd see is a circle or a sphere of very low momentum, low energy particles kind of being dispersed from our collision point throughout the detector. Now, why this is interesting is because, one, it's very unique. We would not expect to see something like that at all. And two, one of the interesting challenges of SOUP is that since it would be so low energy, we would have a hard time distinguishing it between kind of other interactions within our detector, specifically this thing called pileup, which is kind of just noise from the collisions. So what my thesis focuses on is seeing this SOUP signal within our data. Now, are we going to see the signal? Maybe we will, maybe not, probably not, because these theories have to be crossed out, and just that in and of itself is a good endeavor in terms of a thesis to say this SOUP theory definitely does not exist, or at least probably doesn't exist. But the idea is that if we do see this signal, this would indicate not only the existence of the dark sector, but the existence of some sort of dark matter candidate. And so this would lead to hopefully maybe a Nobel Prize, you know,
mhm.
but we're probably not going to get there. And so the idea is to work for, 6 years on this thesis. And I can get into more detail on the research, but the idea is to kind of be able to distinguish what our signal would look like as compared to all the other stuff that we can see in the Atlas detector. And then we look at data. Hopefully we see it. And if we don't, no worries.
Yeah.
But if we do, that'd be
That'd be great.
That'd be fantastic.
Right. For people who are interested in other dark matter related interviews, the interview I did with Dr. Solarski, who's also a Carleton guy, was about emerging jets, which is another Atlas related,
very interesting theory
related analysis.
They actually just came out with their paper, the EG Run 2. Yeah. So that was a big endeavor from Carleton.
It was
fantastic. Yeah.
I was keeping tabs on that just because.
Me too. I was asking Jeremy how are things going. Yeah.
And things kept going wrong for them from what I.
Unfortunately, so listen, I won't speak too much on that, but there were some lessons learned. I've heard.
Anyways, so soup.
Yes.
Theory. Mm-hmm. Any particular reason or like properties of dark matter that would allow it to make this sort of soupy signal?
Well, the idea, that's a really good question. The idea is this is mostly based on more theoretical principles.
As it usually is.
Exactly. So someone like Daniel Stolarski would be
better
to discuss this with. I'm more of an experimentalist, so I'm more focused on the coding aspect. Yeah. But the idea is just the way in which the dark sector particle, which we call the S scalar, would decay through some dark photons. The way you tweak both the dark photon mass, the scalar mass, the overall temperature of the system, it just allows for a very diffuse signal.
Okay.
So I can't speak. I mean, I try to understand the theory myself. I don't think I could explain it to an audience of not PhD students.
That's all right.
But it's very interesting. There are a few papers. It's actually a very kind of underrated theory. There are not too many papers written on it. Which is fun in terms of being able to make your own mark. But it's also quite challenging when you only have 3 papers to look at in terms of trying to see your theory.
So just to make sure that people are following, so the concept of a dark sector is essentially like like a parallel version of the standard model where we have dark photons.
Exactly. So what we call it is QCD like, so quantum chromodynamics like. And the idea is it would just be an analogous universe to ours. So there would be a dark Owen interviewing a dark Will
in a dark universe.
Exactly. The dark quantum Mike. And we have these are all theories, right?
Yeah, of course.
We have no idea exactly how this would look, but a good starting point is, okay, let's say it's our universe, but just inverted. Because you could just say this dark matter is something that interacts with us, but we can't interact with it. And then if that's your starting point, that you kind of
all you got
SOL
is
here. You got nothing to do.
all you got is gravity, and it's like
exactly.
Okay, well.
So you need to assume some sort of messenger between our two universes. What we assume, or what I assume, is the Higgs boson, which is a fine assumption, since it gives mass to matter. It does interact with most things. So it would be a good messenger if that's the case. Maybe it's not. Maybe we're looking in the wrong direction, but you do need to confirm these things.
All you can do is go look. Right?
Exactly. You gotta say, this looks interesting. I'll spend a few years searching it, and then
there you go.
We don't do it for the accolades.
No, exactly. It's for the love of the hunt.
The love of the game.
The love of the game, as some people say. All right. Well, so you're an experimentalist.
I am.
Right? So it's a lot of histograms.
A lot of coding.
Coding, neural network sort of things. So to sort of identify this region, are there any particular analysis elements that you think would be neat to mention or interesting to talk about?
I mean, I think it'd be interesting to give kind of a rundown of what a general analysis looks like at Atlas.
Why not? Go ahead.
Exactly. Yeah. I should mention, just because I didn't give a quick rundown of Atlas, what Atlas is actually is a large toroidal apparatus with the A and the S.
It's a perfect acronym.
It's a terrible acronym, but it's what we got. It gives us a cool logo because we have Atlas with the world on his back.
It puts us near the top of the list.
Exactly. What it is basically it's a big camera. So the LHC, right, this little ring that I explained earlier, has 4 big cameras that get to capture the energy, the momentum, the position of our particles when they're produced from our collisions. And we take snapshots every, 25 nanoseconds, I believe? Or there's a collision.
It's very
quick. It's a very quick camera. Yeah.
We take a lot more data than we store.
Exactly. Yeah. And so the idea is that we take snapshots of these collisions and we try to look at, when you look at a snapshot of this, you just have a bunch of stuff, in your detector, and you have to build up your understanding theoretically of the physics that you're looking at to be able to say, okay, this stuff in this part of the detector has the exact signature of this process. Yeah, and I know this process, so I can say this is not something new. This is not BSN. This is not beyond standard model. Yeah. Right. And so this is the idea of Monte Carlo simulations. So there's a very important step in any atlas analysis is the idea that you want to first simulate your collision as perfectly as possible. Yeah. Because when you look at data, which we call unblinding, which is to just look at actually what's in the detector. Once you look at that, you can't go back. You've already seen, you've taken the curtain off, and that gives you a certain bias. So what we have to do to make sure that when we look at data, it is, if there's something surprising in it, it's not us that messed up, is that we have to spend years and years simulating what we think our process is going to look like, as well as the other processes that might be kind of messy, kind of like, or would be background or similar to our process.
We have there's some very frequent events that occur at Atlas, unlike
frequent events,
more exotic stuff.
Well, the idea that would be somewhat easy, right? If it was okay, we have something that's exotic that we're looking for, and then everything else is kind of boring, run-of-the-mill physics, we can easily filter that out.
That's true.
What we have to understand is, what is this process that we do understand that isn't new, that's kind of boring, but looks almost perfectly like what I'm searching for? Yeah. Because if you miss the two, that's kind of embarrassing. That's kind of the most embarrassing thing you can do in physics. And so what we have to do is, like I was saying, these Monte Carlo simulations basically gives us fake data, simulations. Yeah. And for many years, usually like 5, 6, however long the PhD is, you fit what we call fitting. You fit these simulations, and you're trying to understand how many events or what the yield is per process. So, for example, if I'm looking at a certain process, I expect 20 events per data set, and then for another process, I look at 30 events, something like that. Yeah. Just to get a good idea of what I'd expect to see from my detector, so that when I look at actual data, which can't be distinguished because it's not a simulation, I can't say, oh, well, this is, process A has 20 events, this process B. When you look at data, it's just everything. Yeah. And so what you have to be able to build is a system where you're perfectly identifying process A, process B, process C in your simulations. Yeah. And then you take that mapping and you put it onto your data. So then that way, when you look at your data, you can quickly parse through, this is process A, this is process B, this is process C. Hopefully, we see process W, and we say, oh, we didn't account for process W. Yeah, we have no idea what this is. And then that's new physics. That's very exciting. That's what they saw in 2012. They saw this big bump on their graphs, and they said, this shouldn't be here. This has to be something new. And what we hope would not happen is we see this bump, we get very excited, we say, this is process W, amazing. And then it turns out we just forgot to take something into account, right? Yeah. And so that's why it takes so long for these PhDs to occur, because you have to perfectly, intimately know every single process and really make sure that you're not, messing it up. That you're not thinking you found your needle in a haystack when it's just a very sharp, piece of hay. Yeah. And so that's kind of the idea between all analysis, is that we're just trying to count things as well as possible with our simulations, so that once we look at data, we really perfectly know what's in there, so that if something is in there that we don't expect, we can confidently say, this is new, this is interesting, this is Nobel worthy. And then from there, this whole idea of determining things at 5 sigma, which just means a very precise measurement of things. But the first point is understand everything, so that if anything exciting happens, it's not on you. It's not a mistake you made. It's actually something interesting. Yeah. Because
we can find something interesting, and it can still be, it can be not quite 5 sigma. We can go for 5 or 3 sigma. As long as it's noticeable, it's still worth examining.
For example, we
just need to make it cleaner.
Now, don't quote me on this.
All right.
Actually,
You're being quoted right now.
I'm being quoted right now. Actually, I don't. I think this is internal.
Okay, well then
stuff. So I can't. But we're seeing interesting things. But certainly nothing at 5 Sigma.
Yeah, of course. Right, don't give it away.
I won't spoil. But
it means
it's an exciting field, is what I'll say.
If you find something cool, we bring you back on.
Exactly. Listen,
look at this.
I'll be the second Nobel laureate. It'll be me in art. Yeah.
We can say had him on before he was famous.
Exactly.
Who knows?
And he's still not famous. He just has a Nobel Prize now.
There you go. What sort of, you were talking about signatures that are noticeable for this sort of dispersed jet soup. What would be sort of noticeable signatures for that within Atlas itself?
It's very simple. It's just a diffuse spread, a spherical spread of low momentum standard model particles.
We'd expect it to be like spherical, or can it be like a little bit oblong, or like generally?
I mean, yeah. We have
sort
this. How we measure it is this thing called sphericity, and so it would have some degree of sphericity. Right, so if it's like 90% spherical, then that's fine.
Yeah.
But it's just something we really wouldn't expect to see any sort of spherical distribution, especially at low energy. And specifically, what my analysis is looking for is a hadronic signal, which means we're not looking for hadrons are a certain type of particle.
Yeah. They're like protons, neutrons.
Yeah, exactly.
For the people who are listening, hey, that's what a hadron is. That's why
a hadron,
it's a large hadron collider, because we collide protons.
We're specifically looking for this thing called pions, which is one sort of hadron. And there are other searches at Atlas that look for soup that focus on the muonic channel, so the muonic final state. So things like muons and just muons. I was thinking of the leptonic final state, but of course muonic would just be muons.
Yeah, well, like the tau are gonna decay too quickly, right? Taus
I don't even think
they can.
Well, they probably can't even be produced.
Oh,
right?
yeah,
because
they're like the heavy.
They're the heaviest particles. So
you
need a lot of energy to produce a top, whereas the muons and the electrons are quite little babies, so they're easy to produce.
And the muons will usually get out of Atlas before they decay into electrons.
So that study is not done on Atlas yet, but there is one. The only actually fully done study on soup was by CMS, so our partner detector, which is essentially another big camera at the LHC, but it's complementary to ours. So a lot of the strengths that Atlas has, it doesn't have, and vice versa. And they actually looked for soup. They were the first people to look for soup. Excuse me. And they didn't find anything, unfortunately, but looking at the paper, there are some places that we can both improve and we just have a different detector.
Well,
so it's just worthwhile.
Was it a run 2 analysis?
It was run 2 as well.
Okay, so it's run 3 now. So
exactly. We got more data. We got everything.
Bigger beams,
more protons. There's a very strong argument to do this search, as is for all theses.
Okay.
Really.
Well, I mean, best of luck.
Thank you.
Analysis.
Yeah, 3 years. So let's go.
Before we wrap up, I think there's 2 things we should talk about.
Absolutely.
You're the first grad student I brought on who isn't me.
Fantastic. Okay.
So,
I'm honored.
Yeah. I guess for the people listening who may be interested in pursuing graduate studies, be they physics or not physics, what would be your recommendations or advice?
If you don't absolutely know that you want to do a PhD, start with a master's and don't fast track. Assuming you're in a country where fast track is an option.
Yeah.
If you for sure know, I knew at 7 years old I wanted to do a PhD in particle physics. So I started my master's knowing I was going to fast track. I don't regret that decision. But I do have some friends who are like, okay, I fast tracked. I have 5 years left in my education. If I stop, I don't even have my master's degree.
Yeah.
So that's something you have to keep in mind is, do you want to do your master's first and then your PhD, or do you just want to go gung-ho?
Yeah.
That's the first thing. Second thing is, you do really have to love this. It's not the easiest job. You don't get the best compensation, as you know. So I think a lot of people can be burnt out if they're not absolutely certain that they at least love physics enough to try it. If that is you, if you're kind of uncertain, then honestly just go for a master's, like I said, because that's, should be about 2 years. If you find it's not for you, then that's totally fine. But if you fast track in 4 years in, you're like, okay, I'm done with this.
Yeah.
Well, then you got 2 more years, and then you
get a taste of things in a master's. Right?
Exactly.
It gives you an idea of how difficult things can be, and also,
and also something to keep in mind is, right now, thankfully, I'm finally at a place where I'm doing full-time research. So every day I wake up, I get on my laptop, do my little coding, and I'm as happy as a clam. The past 3 years, I've been doing master's courses, then PhD courses, then qualification exams. So it is a lot of I don't know what the word in English for this is, but in French you'd say paperasse. There's a lot
of stress work.
Well, a lot of hoops to go through.
Oh yeah,
before you can actually just call yourself like a full-time scientist.
Yeah.
And depending on how good you are in class, it might be fun hoops or not fun hoops.
Yeah, and it may take more years or less years depending on when courses are available.
Exactly. Sometimes. I mean, I took a whole year. Well, not off, but I did a full-time year of research just because courses weren't being taught that I needed to get taught. So that's just something to keep in mind, is that if you have this dream of you're going to be a full-time researcher, you're going to wake up and you're going to do science all day and then, go to bed. For the first few years, that's unfortunately not the case. You're still going to be doing a lot of classes. I know when you start a master's, for example, or at least when I started my master's at Carleton, my supervisor, Jesse, was like, okay, year one, we're not even thinking about research. We're just doing classes. We just need to get this out of the way. And then once you get to PhD, they say, okay, you can do kind of half-half, but you need to pass these classes. You gotta stay a full-time student. So that is something to keep in mind. It's both kind of your love of the game. If you really want to be a scientist, then that's fine. But if not, then there are a lot of roadblocks that might frustrate you. And also just the idea of the pay is not great unless you go for these grants such as NSERC and like Vanier, but I actually think Vanier is not a thing anymore.
It's very Canadian.
It's very Canadian, yes,
right? Keep in mind, this advice is coming from Canada.
Exactly.
If you're
in the States, good luck.
Good luck.
You don't even get guaranteed pay, I think, unfortunately.
And you have to go into a PhD. You can't start as a master's student most of the time.
Yeah.
At least in physics, it's your game, and then you can drop out as a master, sort of thing.
I would also say something to keep in mind is, I love physics. I'm a PhD student. I like it. You do need to think logistically because, we are adults. I'm 26. I need to start thinking about, my own bank account and stuff.
Yeah.
You do want to get a sense of, there are some universities that pay better than others. For example, I think Carleton is maybe number 1 or 2 best paid.
We're
pretty up there.
It's actually reasonable.
It's almost
reasonable.
It's almost at the poverty line. We're still below, but it's like, we're almost there. And so that's just something you need to keep in mind is, where you're going to go live. If you do a master's in Vancouver, then your rent is going to be way higher than here in Ottawa. And that is something that you just need to account for and to make sure you have covered, because you don't want to stop your passion for physics just because you can't afford rent. You know what I'm saying? So that's something to take into account, is that this will be your job. And so you need to be in a position to have a low-paying job. The upside is everyone here is passionate. You're passionate. I'm passionate. Everyone effectively loves their job, which is great. But that only that doesn't pay for groceries. That is something to keep in mind. Be sure you want to do it. Start with a master's if you're not sure. Think logistically. Apply for grants. I've met a lot of smart people who, just by happenstance, don't have the time to apply for grants or are too lazy to apply for grants. So apply for grants, because you would be surprised with the things that you can get. And once you get one, then it snowballs into the other, into the second, to the third. So absolutely apply for your grants. Then that's I don't know what other advice to give.
I mean, that's pretty solid. You covered most of the bases as an experienced grad student.
Yeah.
Well, awesome. Thanks again for coming on the show.
Thanks for having me, of course.
But of course, I like to finish up with the question that I ask everyone. Okay. The question, which I primed you for a little bit. But essentially, I was wondering if you could share sort of like a meaningful or impactful sort of experience you've had with regards to science or in the scientific community that you think has been sort of important or,
what comes to mind is, I don't know if this program is still a thing, but back in 2018, there was this thing called CAPS, the Canadian Astroparticle Physics Summer School. And Devin off screen is telling me it's still there. Okay. Anyway, yeah. So like Devin said off screen, it is still a thing. This CAPS summer school, but that was a really nice experience. So that was back when I was 18 years old, second year undergrad. And the idea is that for a week you learn about astroparticle physics, and specifically you get to visit Snow Lab, which is our pride and joy. Is this big underground lab, 2 kilometers underground, in an active mine shaft. It's fantastic.
Canadian CERN.
It's Canadian CERN. It's truly. I mean, it's that in Triumph. People should know about Snow Lab. Anyway,
Snow Labs and Triumph are. You know what? Actually, we should do things talking about those, but another time. Anyways, keep going.
All I remember, or I mean, what I remember is it was a really eye-opening experience of one, just how intense physics is in Canada. How much we have invested, how many opportunities there are. For example, I did a co-op afterwards at Snow Lab, and it was really fun. But also, just how great the community is. I think, there's always the stereotype of physicists as being kind of introverted, maybe a little nerdy, not the most socially adept people. But at this summer school and at the conferences I've been to, most people are actually very outgoing, very extroverted, very excited to see like-minded people. And it's just a fun, open community, which is great, very welcoming. And you find that you can both be passionate about your job and find friends, just have a good time. This whole week-long summer school, we'd learn about physics all day, and then, we'd party all night. It was a great time. And, when we went down to Snow Lab, these are lifelong physicists, 50, 60, 70 years old. And they're all dressed in their equipment, in the clean rooms and everything. We're getting a tour, and they're all just excited to talk about their big toys, about their big, the snow experiment, Halo, not the game, but the experiment. Look it up. And it's just a really nice, welcoming community, which you don't necessarily get to experience too profoundly if you just stay in your undergraduate circle. When you really get to meet other people that are extroverted enough to sign up to these summer schools, to go to these conferences, then you see, okay, everyone's nice, everyone's having a good time, and we're all, they're all smart, we're all, it's great. So yeah, that's something that week at CAPS was a really important time in my physics experience, because it kind of solidified that, I'm gonna have a good time doing this. I'm gonna have a fun time being a grad student, so I would very much recommend any sort of summer school, any sort of conference. Go present. No one cares if you're nervous. Worst case, you go up on stage and say, "This is my first time." No one's gonna be mean, So,
awesome. Well, once again, thank you for coming.
Thanks for having me. Absolutely.
Yeah.
All right.
Wow, that's a tough handshake.
Yeah. Thank you. Listen.
All right. For everyone who's listening, thank you again for watching or listening to an episode of the Quantum Mic. Thank you again for Will for
Thanks for
letting me interview him. And being willing to do an in-person interview.
For sure.
If you enjoy this show and you enjoy physics or interested in science-related things, I would recommend subscribing.
Subscribe.
Like
and subscribe.
Hit the bell. Leave a comment.
Yes.
If you are a physics or science communication or just peripherally related to physics or science and want to talk about your research or your work or something like that, let us know. There should be an email address in the description. And have a good one, everyone.
See ya.
There we go.
Yay!
That's a wrap.
Very nice.